We'll start our discussion of the angular momentum. Okay, we'll continue with it. So last time we looked at the quantum mechanical angular momentum operators, and we found the commutator of Lx and Ly. What did we get? Remember? No. Okay, IH bar Lz, right? Okay, so it's important that angular momentum operators in two different directions do not commute. Okay, so we cannot measure them at the same time. We cannot measure Lx and Ly simultaneously. Okay, so we cannot know them simultaneously. Now, just since all directions in space is supposed to be the same, we can just rotate these things cyclically. Ly, Lz is going to be I h bar Lx, okay, and Lz, Lx is going to be equal to I h bar Ly. Okay, and actually we'll be just using these three commutation relations, and it's amazing how much information we can extract about the angular momentum states just starting from these three commutation relations. Okay, so angular momentum is a vector. Yes?
This vector, we cannot measure them simultaneously. So how do we measure one? Because we also have momentum and space uncertainty and ellipse in a way r cross t, like rotating. So how do we measure one of them?
Well, okay, the question is how do we measure even one of them, since they involve momentum and the position. The point is we have a Hermitian operator, okay, Lx or Ly or Lz, and we are measuring only a single one of them. So as long as you have a Hermitian operator, a single operator, you can find its eigenstates, and eigenstates of that operator are possible results of the measurement. Okay, so in practice, of course, what you do is that if you have a charged particle with some angular momentum, that corresponds to a magnetic moment, and the magnetic moment can be measured by various methods. Okay, in particular, if you put it in a non-uniform field, okay, then there's a force on the magnetic moment which deflects it one way or another. So by measuring the amount of deflection, you can measure, okay, the amount of magnetic moment, which is a measure of the angular momentum. Okay, so measuring the angular momentum doesn't mean you are precisely measuring the x and the px at the same time. Okay, it just is that you are measuring properties of that Hermitian operator. So if you measure Lz very precisely, for example, it doesn't give you any information about x or px or y or py. Okay, so in that sense, there's no problem with that. Okay, so these are three directions that we choose, okay, in rectangular coordinates, three independent directions, and that's what we get. Okay, but we can also look at the total angular momentum. Okay, so the angular momentum squared, which is going to be Lx squared plus Ly squared plus Lz squared. Okay, this is called the total angular momentum. Okay, this is just terminology because actually it's angular momentum squared. But the L squared operator we call the total angular momentum operator. Okay. All right. So we cannot measure these stuff by themselves, but can we, for example, measure any one of these objects simultaneously with L squared? Now, for that we have to check what, okay, for example, LZ with L squared is. Okay, so if they commute, I can then find, okay, common eigenvectors of LZ and L squared. So let's check that, okay? Do they commute? Okay, so how do I do that? Well, let's start LZ with Lx squared, Ly squared plus Lz squared. Okay, so that's what I want to calculate. Now Lz obviously commutes with itself, right? So that part just drops out, okay? The commutator of Lz with Lz squared is 0, right? So this is just going to be commutator of Lz with Lx squared and Ly squared. And so that's equal to commutator of Lz with Lx squared plus Lz with Ly squared. So we have some commutators to calculate, okay? So let's start. What's Lz with Lx squared? Okay, so Lz with Lx squared, let me just write this out. There are certain identities for commutators with products of operators and such things, okay, but I can never remember them. So I just always use the nice long calculation method. So the strategy is, you see I have Lz Lx squared and here Lx squared Lz in long order. Okay, so what I'm going to do is I'm going to walk this Lz one step at a time towards the left so that when it moves all the way to the left, that term Lz Lx squared will cancel that Lz Lx squared. But when I am, okay, moving things around, obviously I'm going to generate some terms, and that will be the commutator. Okay, so let's just do it. I have Lz Lx squared minus, okay, I have Lx times another Lx times Lz, okay? So instead of that Lx times Lz, I am going to put them in the opposite order, Lz Lx, right? But now I have to put in, add to that, the commutator of Lz Lx, okay? So, I'm sorry, Lx Lz, okay? So I have Lx Lz, which has gone to Lz Lx. So what is the commutator of Lx with Lz? Okay, Lx Lz is over here, but it's in the wrong order, so I need a minus sign. So I need a minus I h bar Ly, right? Okay, so I am just one step away from getting an Lz Lx squared, right? So let me just write this out. So what happens? Okay, I'm not sure best way of using the board here, strategy. So Lz Lx squared, okay, let me write this term plus I h bar Lx Ly. And then I have this minus, right, Lx Lz Lx. Okay, so I want to now move this one step to the left, interchange Lx and Lz. So there will be an Lx over here, right? Please check my algebra so that I don't get any funny results. Okay, so LZ, LX with LZ. Okay, this is something we did earlier. So what do? We just put here an LZ, LX, but then put in a commutator of LX, LZ, which we decided was minus I H bar Ly, right? Okay, any questions about any of this? Yes.
How did we do the first one?
How we did this one?
Right.
Okay, so what we have is we are trying to move stuff. Okay, so let's just look at this. We have Lx times Lx times Lz, right? So that's what Lx squared Lz is. So what we are doing is, in place of this Lx Lz, we are putting Lz Lx, but with the commutator of Lx Lz. So remember that this Lx Lz is just going to give me Lx Lz minus Lz Lx, which means that it's going to just cancel this and I'm going to get Lx Lz. Okay, so the rule for interchanging the two operators is, okay, go ahead and interchange them, but then add to them the commutator. Okay, the commutator in the original order. Okay? So, what do we get? We get, okay, Lz Lx squared. So Lz Lx squared, that's very nice. I cancel those things. So what remains here is the commutator. So I get I H bar Lx Ly plus Ly Lx. Okay, so it's not the commutator, there's a plus sign in between, so I can't go any further. Okay, so that's the commutator of Lz with Lx squared. Okay, so I have found what this is. Now I'll look at the second term. Okay, let's figure that out. So let me just remove this. Okay, so now Lz with Ly squared. So same thing. I have Lz with Ly squared. Okay, so that means minus Ly squared Lz. So this time I'm going to walk this Lz one step at a time towards the left, so that I'll get eventually Lz times Ly squared to cancel this. But we'll generate some terms along the way. Okay, so what is that? So let me just draw a line here. Okay, so I'm going to get Lz Ly squared minus, okay, there's an Ly multiplying an Ly Lz. So what do I write here?
Lz Ly plus
Okay, Lz Ly, and then the commutator of L, what? Ly with Lz, yes.
So I didn't understand the second line of the, how...
You mean this one?
Yes, I mean, I didn't understand the second part of where does it come from, these terms.
Where do they come from? Okay, it's always the same thing. You see, I have this Lx times Lz times Lx minus, okay, this term. So this term is that term, right? Okay, so what I have here is an Lx, Lz, Lx, okay? And my aim is to get to something which looks like this. So I have to change this Lx, Lz to Lz, Lx, okay? So what I do is I say this is Lz, Lx minus, okay, the commutator of Lx with Lz. Okay? Okay? All right, so let's go on. So we have Lz, Ly squared minus Ly, Lz. So we are doing it again. In place of Ly, Lz, we are putting in Lz, Ly. And the commutator of Ly with Lz, which is what?
Minus pi Lx.
Lx, right. Okay, so one more step. So we have Lz, Ly squared. Let me keep the minus I h bar Lx, Ly separate. Or I put it the wrong way, Ly, Lx, right? I have to be careful with the order. Okay, so what's the last term? Plus Ly, Lz, Ly, right? Ly, Lz, Ly. Okay, so I'm going to do it slowly. So again, I want to move this Lz one more step toward the left. And how do I do it? I interchange their places, but then put in a commutator of Ly with Lz. Okay, so this term here is going to be Lz, Ly, okay, plus the commutator of Ly with Lz. Okay, so that the Lz, Lys are going to cancel. Okay, and I again have Ly, Lz. Okay, so what do I get? So it's going to be Lz, Ly squared minus I h bar Lx, Ly. And then I have plus Lz, Ly, put another Ly here, squared. And then this thing Ly, Lz is plus I h bar, but I have an Ly. Okay? Now you see I have generated here a term. Okay, did I do this correctly? Because I should get a minus sign, yes. Okay, so this needs to be minus, right? So that I get minus and minus. Okay, so now Lz, Ly squared, okay, cancels that Lz, Ly squared. And I end up with minus I h bar. Okay, what?
Lx, Ly.
Yes, this is Lx, Ly, thank you. The first term is Lx, Ly, right? This one is, let me see what's going on. Yeah, this one is Ly, Lx, right? Okay, I told you to check my algebra. Okay, but in any case, I do have an Lx, Ly, and then I have an Ly, Lx. Okay, so I get, you see, precisely the negative of this one. So going back over here, this is going to be plus I h bar Lx, Ly plus Ly, Lx. The other one is going to be, okay, the negative of that. So when I add them up, I end up with 0. Okay, so this is important. This says that L squared, so Lz commutes with L squared. So Lz has nothing special, okay, Z is not a special direction. So although I have not calculated, I can just say that due to symmetry, all of these commutators, Ly, L squared, they'll all be 0, okay? Because L squared is just spherically symmetric total angular momentum operator. So the commutator of it, if it is 0 for LZ, it must be 0 for LX and LY. Okay, you can check these things for practice, but obviously we are going to get the same thing. In fact, L squared is, again, spherically symmetric. If you construct any component of angular momentum, it doesn't have to be x, y, z. Okay? The angular momentum, let's call it in some direction defined by the unit vector n, is going to commute with the angular momentum. Okay, so choose any direction in space. Okay, you can find a set of eigenfunctions which are also eigenfunctions of L squared. Okay, so I can, yes, excuse me? Okay, so let's in fact make a diagram. Okay, so picture is supposed to be worth 1,000 words, right? Okay, so that means that if I have an object, an atom perhaps, okay, and I want to measure the total angular momentum, I can measure the total angular momentum, L squared, okay, and we are going to get a result out of this, okay? And there are various possibilities. We'll see that these are a discrete set of possibilities, okay? And suppose we find out that the angular momentum is equal to one of these possibilities, the total angular momentum, okay? So let's just postulate the form of these eigenstates. Okay, so I have L squared and LZ. So whenever we choose a direction, our favorite direction is LZ. Okay, if you want to choose a direction among others, we usually choose LZ. Okay, so these things have eigenstates. And what we are saying here is that since L squared and LZ commute, they share a set of eigenstates. Okay, so obviously they are going to have different eigenvalues. So let me put labels on them. Let me call this thing lambda, this one m, lambda m. Okay, why am I putting two labels? Because I'm going to get two different eigenstates, okay, two different sets of eigenvalues. Now, for example, for lambda, I know that it's going to have units of angular momentum squared, and one nice quantity that has units of angular momentum is h bar, okay? So I say that in order to keep lambda unitless, I'm going to say that this is lambda times h bar squared because it has units of angular momentum squared. So lambda is now a unitless number times lambda m. Okay, so this is an eigenstate of L squared with eigenvalue lambda times h bar squared. Okay, we'll try to find out what lambda is. And for the LZ, again, since this has units of angular momentum, the eigenvalue is going to have units of angular momentum. So that I'm going to call mh bar, so that m is again unitless. Okay, same eigenstate. Now, I can do that because I know that L squared and LZ commute. So because they commute, okay, I can find these eigenstates which are common eigenstates to both of these operators, okay? Now, obviously, I could have chosen Lx or Ly, etc., but I cannot choose any two of them. I can choose only one, okay? Because Lx doesn't commute with Lz, Ly doesn't commute with Lz, so that means I am stuck with just L squared and one of the directions, okay? So I have only those two that I have. Okay, so now I am measuring the L squared. And I find out that for a certain measurement, this particle happens to have an eigenvalue, okay, result of the measurement, which is equal to lambda times h bar squared. Now, if I measure Lz, okay, I'm going to get a result out of this. Again, one of these results is going to be m times h bar. Okay, I don't know what m is, but okay, I'm going to get a certain result. Now, L squared and Lz are compatible. Okay, they commute. Okay, so I can now go back and make, for example, an L squared measurement. I am going to get exactly the same lambda. Okay, so same lambda times h bar. Because this now does not destroy the previous measurement because they commute. Yes. H bar squared, thank you. And then I can measure Lz again. And what do I get? Okay, the same m that I got earlier. Okay, so that's what that means, that these things commute. So I can form these eigenstates, which are eigenstates of both. So after the first measurement, what is flying out here, after I have made both measurements, is my lambda m. And now I can make L squared measurements or Lz measurements. They always give me the same eigenstate, okay? I do not have any change. Yes?
Assuming that there is no degeneracy after the first L squared measurement, the Lz measurement is deterministic, right? So
Yes.
it's always
After the first?
L squared measurement. So if we get lambda a squared, then if we make Lz, we will always get mx.
Well, but we are going to get one of these. I don't know which one, right? So originally, I don't know which m I'm going to get here. Okay, so I just know the L squared here. But once I also measure m, now I have determined the eigenstate. Okay, other questions? Yes.
Can't we have Lz squared equals to L squared? Can't we have Lx and Ly 0 since
No.
no, why?
No. Okay, we'll see why. Okay, because they don't commute. Okay, Lx and Ly do not commute. Okay, so if I make, for example, an Lx measurement here, I have lost my m. Okay, because there's now a different measurement. They don't commute. So any measurement here which doesn't commute with these things will destroy the state. Okay, so I'm not going to know what happens. Okay. All right, so I have this structure in this form.
I have a question.
Yes.
Are these eigenstates, do these eigenstates form a base of the state space?
Yes. Okay, so when we find all of these things, okay, when we find all of these eigenstates, all possible eigenvalues, they will form a complete basis for the angular momentum space. Okay? All right. So what do we do now? We are going to we are going to see how these things work out. We are going to introduce two new operators. Okay, so L plus and L minus operators. Okay, so these plus and minus operators, they may look familiar from the harmonic oscillator problem solution, and in fact, okay, they are not unrelated, but at this point, let's just see what they are. Okay, so it's going to be Lx plus or minus, depending on whether I have a plus or minus here, I Ly. Okay, so these are my L plus or minus operators.
Is this for LZ?
No, okay, these are Lx and Ly.
L plus or L minus for which animal momentum?
No, L plus is defined as Lx plus I Ly. L minus is defined as Lx minus I Ly. Okay? So there's no Lz in this. But now we are going to see what happens. Okay, let's just look at the commutator of various things. For example, let's look at L squared with L plus or minus. Let's just look at what L squared with plus L plus is. It's going to be L squared with Lx, okay, plus I Ly. What is this? 0, right? Because L squared commutes with Lx, L squared commutes with Ly, so this is 0. So similarly, if I just put an L minus here, you see all that changes is this sign minus. So L plus and L minus operators commute with L squared. Let's see what they do with Lz. Lz with L plus. Okay, so again, check my algebra. As you can see, I make lots of mistakes. Lx plus I Ly. So what is Lz with Lx? H bar Ly, okay, it's in the correct sequence, Z and X, plus I. What is Lz with Ly? Minus I H bar times Lx. Okay, so this, as you can see, is a plus 1. So it's going to be H bar Lx, okay, plus I Ly. So what did I get? I get H bar times L plus again. Okay. Let's now play around with L minus. Lz with L minus. Okay, almost the same thing, apart from a simple sign change. Lz, Lx minus I Ly. So almost everything will be the same. I H bar Ly for the first commutator. Then minus I H bar Lx. And this time I get a minus sign here. So I get minus H bar. Let me factor that out. Okay, Lx. But then I also need a minus in front of this. Okay, this is Ly, right? Same thing. Minus I Ly. So I end up with minus H bar L minus. Okay, so we are generating lots of relations, but okay, don't worry, it's not really going to be that bad. Okay, so let me just carry some of these things over here. So we'll use this board as our table. Okay, so we have found out that Lz commutes with L squared. Well, I have already written those things. So let's just put these things down. L squared with L plus or minus is 0. L plus or minus, let me put that over here also, is Lx plus or minus I Ly. And also I have Lz with L plus or minus is equal to plus or minus H bar L plus or minus. Okay, so if I have the commutator with L plus, I get plus H bar times L plus again. If I just do the commutator with L minus, I get minus H bar times L minus again. Okay? All right, so let's now just see what happens under these circumstances if I apply this L plus or L minus operator to one of these eigenkets. Yes.
I think there is something on the eigenkets. For the first one, we have something, and we multiply this eigenvector, and we end up with some vector with coefficient of lambda times h square, right?
Yes.
So after we go through with LZ, shouldn't we end up with lambda times h square multiplied by n times h?
No, it's just one operator, okay? So I am making an LZ measurement. An LZ measurement means I get one of the eigenvalues of LZ. Okay? So LZ has these eigenvalues, mh bar. So I'm going to get just one of them. Okay?
For the first case, we end up with L square bracket of something, and we end up with some coefficient, and so we go to, shouldn't we?
No, okay, this is, you see, this is, no.
Whatever
Okay.
this coefficient,
No, this sequence is not carrying out an algebra, okay? This is not just multiplying it by this, okay? This is the result of this measurement. Maybe I should put it very close here. Okay, so this is the lambda h bar squared result. So there are various possibilities. So lambda can be one thing, another thing, another thing. So one of these possibilities is one of the lambdas, okay? So I make a measurement and I find out that this is equal to, I don't know, 5 h bar squared, okay? Actually, it's not possible, but let's assume it's so. So it's that, but the state that's flying over here now is going to be lambda and m equal to something that I don't know. Okay, that's the eigenstate. Okay, now over here, mh bar is one of these possibilities. Okay, but the eigenstate is now determined because I now know both lambda and m. Okay, because this measurement told me what m is. Okay, it doesn't change the previous measurement. It doesn't change lambda because L squared and LZ commute. Okay, because they commute, this initial measurement of value of lambda is going to be that. Okay, so think of, if you are having problems with the unfamiliarity due to angular momentum, consider two other operators that commute. For example, x position and y position commute, right? I can measure them independently. So if I measure the x position of a particle to be 3 centimeters, then I measure the y position of the particle at 5 centimeters. Okay, so x is still 3, y is 5. Okay, and no matter which way I measure them now, I'm always going to get these two results because they commute. Okay, they are compatible measurements and they don't interfere with one another. So this is the same thing. The total angular momentum here, whatever it is, okay, it's lambda times h bar squared. I have measured it. And this measurement doesn't interfere with that, okay? It doesn't destroy it. So that still stays, but I now have more information, okay? Because now I also know the z component of the angular momentum as well, okay? Other questions? Okay. Thank you. Yes.
For example, let's say L square has a degeneracy in the same eigenvalue and LZ has not.
No, those things do not happen. Let's see what the angular momentum looks like, okay? Because it's well defined and we'll see what it is. Okay, so let's now see what happens when I take this lambda m eigenstate, okay, and operate on it with L plus. Okay. So this is now some other ket, right? This is an operator, operates on this ket, and I get another ket. So let me just see what its properties are. First of all, let me see what happens when I operate on it further with L squared. But I know that L squared and L plus commute, right? So I can write this as L plus L squared lambda m. And that gives me L plus L squared times lambda, I know is going to be lambda times h bar squared lambda m. Okay, and this then tells me that this is equal to lambda h bar squared times, okay, this L plus lambda m again. So looking at the first line, okay, the first equation on the left and the one all the way on the right, what does this tell me? Mm-hmm. Yes, so this object, okay, is an eigenstate, okay, of L squared, okay, with same eigenvalue. So I have found another eigenket, okay, with same total angular momentum. Okay, so remember that this L squared is for total angular momentum. I know that this has, okay, this piece alone is lambda squared lambda m is h bar squared lambda m again, right? So this piece here is an eigenstate of L squared with eigenvalue lambda h bar squared. Okay, so now when I operate on it with L plus, I'm going to get this new eigenstate. Let's see what it does to Lz. Okay, so L plus lambda m is going to be equal to, okay, so now I have Lz, L plus, okay, lambda m. But now I have a commutation relation between Lz and L plus, which gives me plus h bar L plus, right? So let me do that commutator. I'm going to replace these things. So how do I do it? I replace them, okay, I interchange them, L plus Lz. What do I add to it? I have Lz, L plus.
H bar L plus.
Okay, I have to add its commutator, which is h bar L plus. Okay, lambda m. All right, but now Lz operating on this, because it's eigenstate, is going to give me m times h bar. Okay, so this will be equal to L plus m times h bar, when it operates on that, plus h bar L plus, okay, times lambda m. Let me pull out everything except the L plus, okay, so this is going to be m plus 1 h bar, okay, times L plus lambda m. Okay, so now looking at this, what does this say? What's the physical meaning of this? Yes.
L plus is again an eigenstate of Lz with an eigenvalue greater by 1.
Yes, okay, so this is, okay, an eigenstate okay, of LZ with eigenvalue, okay, m plus 1 times h bar. So in summary, this says that L plus times lambda m is equal to, I can't say equal to, all I know that it's proportional to, okay, same lambda, okay, same total angular momentum, but one higher, okay, eigenvalue, one higher m value, okay? Now, I'll not do the L minus, so it will be a big suspense for you what it is. What's it going to be?
M minus 1.
Okay, so it's going to be proportional to, this is exercise. Okay, just do this, okay, go through this, lambda m minus 1. So these things are again called the raising operator and lowering operator. So what have we found? Let me just summarize the spectrum over here. For any value of lambda, yes?
Since L square must be greater than LZ square, can this raising or lowering destroy the state as well?
Yes, okay, so let's just look at the structure first. Okay, so we have found that if we have a certain value for LZ, okay, so I am looking at possible values that can be generated by this LZ, and we postulated the presence of this M. Okay, so that corresponds to an LZ value of mh bar. Okay, so that's one possibility. Suppose I can find just one eigenstate like that. Now, when I operate on it with, okay, L plus, we are going to get an m plus 1 h bar. If I, L plus. If I operate on it with L minus, I'm going to get m minus 1 h bar, okay? So I have a spectrum of eigenvalues separated from one another by h bar. Okay, so I have a bunch of eigenvalues like this. All of them, okay, so all of them correspond to an L squared, okay, associated with lambda times h bar squared. Okay, all of them have the same total angular momentum because the total angular momentum did not change. So we have the total angular momentum equal to some quantity, but various possibilities for the z component. Okay? Now, obviously, this cannot go all the way, okay, from minus infinity to plus infinity because the total angular momentum is restricted, right? You cannot have something more than the total angular momentum. So there will be something here, some maximum value, okay? So L is, let's call it small l, m max, okay? But from symmetry, if it has some absolute maximum at plus value, it must have the same value, okay? So it's going to be minus L equal to minus m max, okay? And if I try to lower this anymore, I'm going to get 0, or if I try to raise this with an L plus, I'm going to get 0. Okay, so this is going to be restricted between minus L and plus L.
Why it's minus? Why?
But it can't be negative also, right? So I can go lower and lower, but L squared, of course, is the square of this. So if there's a limitation on the size of this, it cannot become too negative also. Okay, so it has to be between those two limits.
Can we say L naught L is equal to lambda times h square?
Okay, well, unfortunately we are out of time, and those exciting questions will have to wait until when? Thursday. But we'll see how all of this fits in. But it's just amazing, just from the commutation relations we can get all of this, and we are going to get a lot more out of those commutation relations. Okay, so we'll meet on Thursday morning.